Hello all, welcome back to Sri Sai Tech Edu YouTube channel. Read, Lead, Success. I am dealing with the subject Network Analysis and Control Systems. I have already uploaded Module 1 to Module 4 videos. If you have missed out, please do watch. In Module 5 also I completed first 3 chapters. Today in 4th chapter of Module 5 we will learn a concept. Under Nyquist plot, we have seen already two concepts, that is principle of argument and Nyquist stability criterion, and how to draw the Nyquist plot, and problems also we have seen. In this video, I am going to do the assessment of relative stability using Nyquist criterion. Assessment of relative stability. Okay, we will see problems also on this. Assessment of relative stability using Nyquist criterion. The Nyquist plot provides information about absolute stability as well as relative stability. Nyquist plot, what it provides? Absolute stability as well as relative stability of a control system without any need to determine the location of the closed loop poles, that is the roots of the characteristic equation. The relative stability of a closed loop system which is open loop stable can be measured by using Nyquist plot. The relative stability of a closed loop system which is open loop stable can be measured by what? Nyquist plot. Since the stability criterion is merely of the non-encirclement of -1 plus j0 point, the stability information of a system can be obtained by merely looking at the polar plot, by using polar plot. As the polar plot gets closer to -1 plus j0 point, what we have seen in the previous video, that is -1 plus j0 point means, should understand, that is this is the point -1 plus j0 point, the relative stability reduces and the system tends towards instability. If the polar plot gets closer to this point, the relative stability will what? Will get reduced and the system tends towards what? Instability. So it should not happen. Which should not happen. Figure 8.18 shows what? The two systems with their dominant poles and their polar plots. We know that system A is more stable than system B. Why? See, system A has all its poles at the left side of the location, so that system A is more stable. And if you see one more thing, here also it is left side only, but it is not stable. Why? Because here it is approaching to -1 plus j0 point, but here it is not approaching towards that point. So if it is the system B is approaching -1 plus j0 point, means what? It is instability. That is nothing but A is more stable than B, because its dominant poles are relatively far away from j omega axis than those of B. It is far away from this j omega axis system A, and as well as it is approaching what? This is approaching towards the point which is not approaching towards the point. Observing their polar plots, we can conclude that as the polar plot moves closer to the -1 plus j0 point, the system closed loop poles move closer to the j omega axis, right? And hence the system becomes relatively less stable and vice versa. So this is the system which is not stable. A is more stable than B, more stable than B. Figure 8.19 shows the polar plot of g of s into h of s, which is in the form of 1 by s into 1 plus t1s into 1 plus t2s. It crosses the negative real axis. It crosses the negative real axis at a frequency omega equals to omega 2. It is crossing the negative real axis at omega is equals to omega 2 with an intercept of what? A. With an intercept of what? A. Intercept is nothing but with the distance from the j omega axis. Intercept of A. Let the unit circle centered at the origin omega centered at the origin, obviously it passes through what? -1 plus j0. Let the unit circle centered at the origin, what happens? Obviously it passes through -1 plus j0 point, intersect this polar plot g of j omega into h of j omega locus at a frequency omega equals to omega 1. Omega equals to omega 1. Okay, this is the polar plot at frequency omega equals to omega 1. So let the phasor g of j omega 1 into h of j omega 1 make an angle of phi with negative real. See, it is making phi with negative real axis measured by positively in the counterclockwise direction, means anti-clockwise. This is the anti-clockwise direction. No? So anti-clockwise direction. It can be observed from figure that g of j omega, h of j omega locus moves closer to minus 1 plus j0 point. The relative stability reduces. If this point is moving towards this minus 1 plus j0 point, then the relative stability what? Reduces. Simultaneously, the value of intercept A approaches unity and phi tends to 0. What happens? The A approaches 0. A approaches 1, simultaneously A approaches what? 1, and phi becomes what? 0. If the point is moving towards what? Minus 1 plus j 0. So the relative stability could thus be measured in terms of intercept A or the angle phi. These concepts are used to define gain margin and phase margin as practical measures of relative stability. It should also be noted that concepts of GM and PM are applicable only to what? Open loop stable systems. It is only applicable what? For open loop stable system, not closed loop. Of course, most of the practical systems lies in this category only. Gain margin and phase margin. Gain margin. Gain margin is defined as the factor by which the system can be increased to drive it to verge of instability. Is the factor by which what? The system gain can be increased to drive it to the verge instability. Then we can see that in this figure, the same figure what we have considered, when omega equals to omega 2, the phase angle is 180 degree. See here, the phase angle is 180 degree and magnitude is what? A. If the gain of the system is increased by a factor 1 by A, if it is increased by 1 by A, then g of j omega, h of j omega at omega is equals to omega 2 will become what? A into 1 by A. That is what? 1. A into 1 by A. That becomes what? 1. Hence, g of j omega, h of j omega plot will pass through the point this will pass through the point minus 1 plus j 0, driving the system to verge of instability. Therefore, the gain margin may be defined as the reciprocal of magnitude at frequency at which the phase angle becomes 180 degree, minus 180 degree. So, the gain margin should be less so that what? The stability will be increased. If the gain margin is increased, what happens? Then if the system is increased by a factor 1 by A, it is increasing. What happens? What happened? The instability increased. The verge of instability increased. So the frequency at which the phase angle is minus 180 degree is called the phase crossover frequency. Same like Bode plot, we have phase crossover frequency and gain crossover frequency. What it means? That phase angle becomes 180. The frequency at which the phase angle is minus 180 degree. If the phase angle is minus 180 degree, then it is called the phase crossover frequency. With reference to figure, Gm is equals to what? 1 by A. Okay. Then A is equals to what? G of j omega, h of j omega in the form of magnitude, omega equals to omega 2. In dV, the increase in gain for this plot to pass through minus 1 plus j0 point is given by Gm is equals to minus 20 log A dV. Okay, since A is less than 1 for stable systems, log A is negative and hence Gm is positive. Okay, see, for the stable systems, A will be what? Less than 1. Less than 1 is nothing but either 0 or minus in minus values. Log A will be negative and hence system is what? Obviously positive. Phase margin. The frequency at which g of j omega, h of j omega equals to 1 is called gain crossover frequency, right? It is given by intersection of g of j omega plot and the unit circle centered at the origin as shown in figure. This is the unit circle centered at the origin. At frequency omega equals to omega 1, the phase angle is what? Minus 180 degree plus phi. minus 180 degree plus phi. If an additional phase lag equal to phi is introduced at the gain crossover frequency, the phase angle will become what? Minus 180 degree, while the magnitude remains what? Unity only. So the g of j omega and h of j omega plot will then pass through what? Minus 1 plus j0 point, driving the system toward instability again. So this additional phase lag is known as what? Phase margin. Okay, that the additional phase lag what you are adding will make the system unstable. So the phase margin is therefore defined as amount of additional phase lag at the gain crossover frequency required to become the system to verge of instability. The phase margin is measured positively in the counterclockwise direction from the negative real axis. The phase margin is always positive for stable feedback systems. The phase margin will be always positive for stable feedback system. The value of phase margin for any system can be computed what? Angle of j omega, h of j omega, which is equals to 5 pm at the gain crossover frequency plus 180 degree. If you do, you will get the phase margin. For a system to be stable, both its GM and PM must be what? Positive, what we have seen before. In most practical systems, a good GM ensures a good PM, vice versa. If GM is good, PM is good. However, the cases of systems with a good GM but a poor PM and systems with a good PM but a poor GM also exist, as shown in figure 8.21. In second order systems, GM always remains fixed at infinite values, as the plot always reaches the real axis at the origin. It will reach at the origin. So while the PM reduces continuously with increasing system gain, as shown in 8.23. Okay, then in such cases, PM is correct and ensures that in such cases, PM is the correct measure of relative stability. Usually, it is the phase margin which is specified as measure of system performance in design. One more I missed out here is that, see, PM is also exists. This is 8.1 where good GM but a poor PM. Good GM but a poor PM. Here it is a good PM but a poor GM. So, how the polar plots are constructed is shown for all the three cases, where good PM and good PM and poor GM and good GM and poor PM of a second order system where GM is always equal to infinity while PM reduces continuously with increasing gain is also shown. We will see the examples. First example, determine the gain crossover frequency omega g. We want what? Gain crossover frequency omega g, phase crossover frequency omega p, gain margin gm, phase margin pm with the open loop transfer function. As it is told, only for the open loop systems we are going to find these equations. G of s is what? 1 by s into 1 plus s into 1 plus 2s. Comment on the stability of the system. Okay. So, determination of phase crossover frequency omega p and gain margin for the given sinusoidal transfer function. How to convert it? You should convert s in terms of what? J omega. Same way for Bode plot, we are doing the same for this also. We are converting into j omega in the form of frequency, where 1 by j omega, you will convert all s's into j omega. If you simplify, you get a final equation like this. At the phase crossover frequency omega p, the imaginary part of j omega is 0. Hence, put w is equals to omega p in the imaginary part and equate it to 0. Means the imaginary part here is what? Omega p into 1 minus 2 omega p square equals to 0. Means omega p is not equals to 0. The whole thing is equals to 0. So 1 minus 2 omega p square equals to 0. Omega p square is equals to what? 1 by 2. 1 by 2. So omega p is what? 1 by root 2. That is 0.707 radians per second. Means gain crossover, phase crossover frequency is 0.707 radians per second. It is done. Just what we did, we equated it to 0, the real part, by making omega equals to omega p. The gain margin is defined as the reciprocal of magnitude of j omega at the phase crossover frequency. Just a reciprocal means 1 by j omega at omega equals to omega p. Means 1 by minus 3 omega square. Reciprocal of the real part. Real part is what? This 1 by minus 3 omega square. So 1 by 1 minus 1 by 1 by minus 3. It is reciprocal, no? So what you will get? 3 omega p square, which is 3 into the value omega p. You will get 1.5 as the gain margin. So GM in dB, how you will get? 20 log gain margin will be what? 20 log 1.5. If you use calculus, you will get 3.5 dB as the gain margin. Once you found out the phase crossover frequency, you need to find the gain margin by reciprocaling the g of j omega. At omega is equals to omega p. Okay, that to real part of it. Imaginary part equals to 0 for omega p. Then determination of gain crossover frequency and phase margin. Okay, in the same way we will convert, we get some value g of j omega we will do, and 1 by omega, 1 by, here it is same, j omega 1 plus j omega 1 plus 2 j omega 1 by, and from this how it is written here is omega, it is at the origin, so angle will be 90, and then the angle for this will be tan inverse of omega, angle for this will be tan inverse of 2 omega. It is written in that way. So g of j omega will be what? 1 by omega root of omega 1 plus omega square root of 1 plus 4 omega square. Then g of j omega angle will be what? Minus 90 minus tan inverse omega minus tan inverse 2 omega. At the gain crossover frequency, what will be? G of j omega will be unity. So therefore this g of j omega, in the place of omega I will just put omega g, which will be equals to 1. Solving the above equation will be tedious. Hence by trial and error we can find the root. How to find the root from this error? Just put omega equals to 1. When you put omega equals to 1, you will get what? 0.3. When you put omega equals to 0.5, you will get omega, then you will get g of j omega as 1.26. So from the above two calculations, we can conclude that the unity magnitude will occur for a frequency between 0.5 and 0.5 and 1. You will get unity magnitude between 0.5 and 1. So you try with between values, it is 0.6, you will get 0.115 and 0. So you reduce little bit omega, that is 0.57. If you do exactly, you will get 1.00, nothing but unity magnitude you will get. So that will be the root. So let omega equals to 0.57 be the gain crossover frequency. That will be the gain crossover frequency. Since for this value of omega, the magnitude of j omega approximately equals to what? 1. Therefore, gain crossover frequency will be this. So to find the phase margin, what we will do is phi g is equals to, you have the minus 90 minus tan inverse omega tan inverse 2 omega. As you already found that omega equals to 0.57, just substitute 0.57 in the equation, you will get minus 168 degree. So therefore the phase margin, exact phase margin when you get is that 180 plus the phase of the gain margin, that is minus 168. You will get what? 12 degree. So since the GM and PM are positive, the system is what? Stable. As we studied, when GM and PM are positive, the system will be stable. Second question. The open loop transfer function of a system is this. Determine what? K, so that the gain margin is 6. Determine K, so that the phase margin is 40. Thus given the gain margin and phase margin, they are telling us to find the value K for both the cases. So A, determination of K for specified gain margin. Given that G of S is equals to given, so S is equals to J omega, you will convert anyway K by J omega and 1 plus J 0.1 omega 1 plus J omega you will get. Then if you go on simplifying by multiplying inside, you will get an equation. Then at the phase crossover frequency, what we will find? The imaginary part will be 0. The imaginary part is what? Omega into 1 minus 0.1 omega, where omega will be equals to omega p. We will write why, because we want phase crossover frequency, where you will get omega p as what? 3.162 radians per second, while by reducing it. Then g of j omega at omega equals to omega p. Then you will get what? The real part of the thing is what? By the reciprocal, that is k by minus 1.1 omega square. K by 1.1 into the value what you got? is what? Omega square, that is 3.162. It is what equals to 10. So you will get 0.090 K. Okay. So the given GM is what? 6 GB. So 20 log GM is equals to what? 6 GB. Okay. Log GM is equals to what? 6 by 20. GM is equals to what? 10 power 0.3. When you are converting log to this side, it becomes 10 power 0.3. You will get 1.9953. Okay. So the GM value is this. So once the GM value you got, gain margin is already given. So that the gain margin is 6 GB. The gain margin formula is this. From this you got the gain margin. So once the gain margin you got what you can do is substitute back to the phase crossover frequency formula, where 1.9953 by 0.090 K. What you will get? The K value as 5.513. Second question. Determination of K for specified phase margin. So same way, what we will do, at the origin it is there, so angle will be 90, and tan inverse 0.1 and tan inverse omega you will write, right? Then what you will do, by substituting, these angles will be separately added, minus 90 minus tan inverse 0.1 omega minus tan inverse omega. Same like Bode plot, only we are going to take this. So let omega g be the gain crossover frequency and phi g will be what? Resultant phase at the gain crossover frequency. So the resultant gain, how you will find? By taking these all things. By definition of phase margin, the phase margin will be what? 180 plus phi g, what we will get. So required PM is already given, that is 40. So if you equate 40 to this, what you will get? That some equation equals to tan inverse 0.1 j omega g, tan inverse omega g equals to 180 minus 90 minus 40, that is equals to 50 you will get. After that, on taking tan on either side, if you take tan on either side, it is in the form of what? Tan of A plus tan of A plus B, means tan A plus tan B by 1 minus tan A tan B. So as it is tan inverse and you are multiplying tan and tan inverse will get cancelled. Here you will get tan 50. So if you substitute this, you will finally get omega g value. It is in the form of the equation. So what you can do? You can use formula minus b plus or minus square root of b squared minus 4ac by 2a, or you can even find using calci, you will get two root values. On taking positive value, we want positive value. If you take positive value, that is minus 9.228 plus 11.187 by 2, you will get what? Omega g as 0.98 radians per second. As you know, to find the phase crossover frequency, what we will do is that gain crossover frequency, what we will do is that g of j omega, the part of k by omega g root of 1 plus 0 point omega square root of 1 plus omega g square equals to magnitude we are going to write. So k will be equals to what? This. As you already got the gain gain crossover frequency, omega g, if you put it in this, you will get what? 1.378. So K values are, for GM 6 GB, you got K value as this. For PM of 40, K value is this. This is the way you need to calculate. Nothing, you should just equate it to 0. Just substitute, equate it to 0 and equate it to 1. Like that, if you do, you will easily get the values. You just substitute, you will get the K values. The same procedure you need to follow. So this completes what? The assessment of relative stability using Nyquist criterion, and also I have discussed some two sums. The same way, if there are if you have any other doubts, any sum, if you have doubt, you please comment in the comment box. And if you have any doubts till now in this subject from module 1 to module 5, you can just put it in the comment box. See, now we have already done all the 4 chapters of the module 5. This successfully completes all module 5 of module 1 to module 5 of network analysis and control systems in my channel. Thank you from Sri Sai Tech Edu YouTube channel. Read, lead, success. Keep reading.